Hi there, welcome to another tutorial series presentation. My name is Charles Sugasfani Msipa. Our topic today is growth, decay, and the introduction to differential equations. Let's look at this fact here. This is a fact about study of population growth. The fact says that it has been established that populations grow at a rate which is proportional to their level at time t. What does that mean? Now, when we talk of a population, we can represent the population as a function of time. In this case, let's use in general, let's say a population is represented by a function of time y of t. So then what is said here in this statement is that if we look at population growth, you'll observe that the rate of population growth is proportional to the level of the population at time t, what we call here y of t. But from what we've already learned in our previous topics, that rate of change, in this case it will be rate of change of the population with respect to time, can be denoted by y prime of t. So this gives us the rate of population growth with respect to time. So what is said in the statement here is that the rate of population growth is proportional, which normally we express as follows. We'll say the rate, which is y of t, is proportional, or say directly proportional, to the population at the time t. This is the rate of population growth that we denote y prime. So then this actually tells us that when we say one variable is directly proportional to another, we actually mean that there exists a constant, let's say constant k, such that we can express y prime of t equals to k times y of t. That's what that translates to. Now, what we've got here, because of the this is an equation. You can see it has got the left-hand side and right-hand side joined by an equal sign. So in this case, this type of an equation, because of the appearance of the derivative, this would be called a differential equation. I repeat, this type of equation, because of the appearance of the derivative in the equation, we call this a differential equation. And of course, we know that equations, we've got unknowns. In this case, our unknown, which when we solve this equation, we'll be searching for, it will be the expression of the function y of t. I hope you understand that. This is a differential equation, and we know that the equations in general are two-sided expressions with joined by equal sign with an unknown. In this case, our unknown here is y of t. So let's put here y of t is our unknown that expresses that. Now we are in the presence of a differential equation. Let's see how can we solve this differential equation. Now, what we can do here, we can divide both sides by y of t. We'll get an expression like y prime of t over y of t equals to k. I hope you notice that the equation I've got here is actually equivalent to this equation. But this kind of structure is a structure we've seen before, which we can express this way as 1 over y of t, the function we said here is unknown, multiplied by the derivative of y of t. I hope that from our previous discussion, you should be now, this should be ringing bell. What kind of functions are we dealing with here if we are having this kind of an expression? So let's go further now and try to solve this equation. So we have y prime of t over y of t equals to k. So what we can do here, I think to find y of t, we need to introduce integration on both sides of this equation. In other words, we'll be integrating y prime of t over y of t dt equals to integral of the constant k with respect to t. So now, having this kind of expression, I think we can go back to our integration by substitution. We can now say let our u be equals to y of t. Remember, substitution, we use it as a kind of a technique to try to reduce our integrals to kind of standard integrals which we start with. So in this case here, we'll say du dt would be equals to y prime of t. We're differentiating both sides here with respect to t. And then we get du equals to y prime of t dt. So to simplify this integral now, we can substitute this by, which is the numerator here, by du. Then we get the following integral. Du over u, since our y of t is our u, equals to integral, let's say equals to k, because k is a constant, integral dt. Now integrating both sides here, I think now you can see what we've got here. We've got du over u, which we know that this integrated to ln of u. Then this side it will be equals to k t, t being the integral of 1 here, and then 1, we know that 1 is equals to t to the power 0, so we can integrate that using power rule. Let's say we integrate using power rule. This is this will be t to power 0 plus 1 over 0 plus 1, which will give us t. You can check that slowly. Then we can add here a constant c. Sometimes you'll see people add constants on both sides here, but it's not really necessary. I'll always add c on the side of the independent variable t, because this function we're integrating here is function of t, and here I'm integrating to t, so I will integrate this, or I will add c only on one side here. But even if you add it on both sides, you will end up with one constant anyway. So now at this point now, what we can do now, we know that our u is y of t, so we can rewrite this substituting backwards as ln of y of t equals to k t plus a constant c. Now what we need to do is to, like we said before, that our y of t is our non-function. Now at this stage now we're in a position to find an expression for y of t, which we can do as follows. We can apply e, the exponential function e, on both sides here by taking the exponential function of ln y of t equals to e k of t plus c. So now applying the the fact that e and the ln are inverse functions, we know that here we're going to get the argument y of t independent of ln and e just as y of t. And this side simplifying using rules of exponents, we can get e k t multiplied by e to the power c. And we know that e, if c is a constant here, e to the power c is a simple constant which we can write here. Let's say a, I'll write this as a0. You will see later why I'm writing this as a0. So which means this expression is going to be equals to a0 e to the power k of t. So which means now the expression which I'm going to write here as y of t equals to a0 e to the power k t is the expression for the population as a function of time. And you can clearly see that it tells us that a population is given by an exponential function of a natural base e. And the constant k is called the growth constant. So k here defines what we call the growth constant. And as you can see here, if I evaluate this function at 0, now I'll be looking at the population at the time I start observing the population. I was at the initial time where I can start counting. I will call that t equals to 0. So if we now evaluate function y at 0, we're going to get this as a0 e to the power 0, since it's going to be k times 0 there, and this is going to be equals to a0. Hence I said I decided to use this parameter here, a0, which will mean that that will be the initial population when we start observing the population. Then this will give us the population at a time t. So now let's discuss this further by looking more closely at this exponential function. Okay, what we have as an expression for population is y of t equals to the initial population times the exponential function e to the power kt, where we've said k is our growth constant. Now, there are conditions which you can actually consider for k. For example, if we've got k greater than 0, then we know that this kind of exponential function will give us a graph of this nature. It will start initial population at t equal to 0. It will be a0, that is at t equals to 0. Then after that, the population graph will grow exponentially like that. Then we call that exponential growth. Here we've already said that this is the population is described by exponential function, but sometimes a population cannot be necessarily increasing, but it could be decreasing. In this case, the population will decrease when we've got the value of k less than 0, and in that case we're going to have a graph of this nature. Our horizontal axis is our time, so let's say we've got our initial population at t equals to 0 at a certain level here, a 0, and then we know our exponential growth, our exponential decay, then will go, we've seen this previously, will be a graph which goes this way. And then this kind of situation will now be called exponential decay. You must be careful here. Sometimes when you've got this kind of phenomena, people can just talk of exponential growth to mean both decay and growth per se. But what you must be careful, what exactly is being talked about, you must look at the growth constant k, whether it's greater than 0 or it's less than 0, so then you can make sense of whether the population is really growing or the population is decaying. In other words, the numbers of the population are going down. So I think this is enough for introduction. But before we can go further, I would also like to discuss the fact that, let's say this population is growing. So one question which is very interesting in this situation is to ask, when is this population going to be equals to 2a? In other words, when is the population going to double itself since it's growing? And it's expected, because if the population is growing, we should expect at some time t, the population will be equals to 2 times a. That is in the case of growth. And also on the other side, when we're looking at the population which is decaying, which is going down, one could ask a similar question, that if the population started at a equals to 0, when is the population going to be half of what it is now? Now you can find a middle point between 0 and that now. So that graphically we can represent that this way. If we mark point half here, which means at some time here, t, which is initially not known to us, the population will be half of what it is. Similarly, this side, if we've got 2a somewhere there, 2a0, we would expect that graphically, if we move horizontal like this, then we would expect that sometime t here, the population will be double. So let's see how can we look at that. Okay, let's say we're given the expression of population y of t is equal to a0, our initial population, multiplied by e to the power k. So we said here, let's consider that the population is growth, and we want to check when is the population going to be 2a. So we know that at some certain time t, this population is going to be 2a0. But in this case, our t is our unknown. So this takes us to creating an equation here. We know that at that population, at that time t, which you don't know, the population will be 2a, which means this expression is going to be equals to 2a. So what we can do now, we can say 2a0 is equals to a0 e to the power k t, and then what we can do here, we can see that a here, we can divide both sides by a, then we get 2 equals to e to the power k t. And then in this case, remember our unknown is t, and the t there is in exponent. So to make it subject to formula, we need to apply ln on both sides here. This is going to be ln of 2 equals to ln of e to the power kt equals to kt. Now, from this and that part, we can now make T subject formula, which means then T is going to be equals to ln of 2 over k. So in other words, if k is known, then this expression will give us the time at which the population is going to be double. But also, in some problems, you might find that you are given some information, but you don't know the value of k. So you can see here that as bonus, we can also derive the formula for getting the constant, the growth constant k, by saying k is equals to ln of 2 over t. In this case, t will be given, and that the only way we can get t here is when k is given, and also this side, the only way we can get k here, if k is unknown, is when t is given. So that will depend actually on the problem which we'll be solving at that particular time. So similarly, we can also look at the case when k is less than 0. Otherwise, for now, I would like to say thank you for listening.